So, at this stage in our journey into chemistry and art, we have pointed out a lot of the colors that metals cause when we went through and talked about pigments. And we're revisiting that as we talk about glazes, and we're saying, hey, these metal ions cause there to be color in glazes. And so, what I hope that you're starting to ask yourself is, well, what is it about these metal ions that cause them to have color, right? So, what causes color in these metal ions and pigments and glazes? And so, hopefully, at this point, you've asked yourself, what type of elements did you usually find in the chemical formulas with these natural and synthetic pigments that we looked at previously, and then glazes? And my hope is that you noticed the trend where it was mostly transition metals. So it was things like copper, right? Copper 2 plus. We looked at copper patinas in lab. Those gave us greens and blues depending on the copper complex. Iron, right? And Prussian blue. We saw that as well. Um, both Fe2 plus and Fe3 plus. So lots of these transition metals give color to the glazes. And so, well, why do they do that? I also want us to look at the source of glaze colors here. And I want you to notice how they're similar to the glass colors that we looked at in the previous screencast. We've got irons here, we have coppers here. Cobalt gives us that really pretty blue. Coppers give us blue and greens. Iron oxides give us a wide range of color. We've got green to amber. Chromium oxides give us a wide range of color. And a lot of this depends on what their charge is on chromium. We've got manganese, nickel, vanadium. All of these are right there in that transition metal block. So let's review color and why we see color for just a second. So, the human eye perceives a mixture of all colors in the proportions present in sunlight as white light. So, the colors that we see all around us are the effects of that white light hitting objects and being partially absorbed. Um, and that remaining light that's not absorbed is reflected to our eyes. Okay. I also want to remind you about complementary colors. So, complementary colors are those that are located across from each other on the color wheel. We talked about this in our color module. And the eye can perceive a mixture of two complementary colors in the proper proportions as white light. So, not just all the colors, but sometimes it can just be two. Likewise, when a color is missing from white light, the eye sees it as its complement. So, for example, when red photons are absorbed from the white light, we're going to see that color as green. When violet photons are removed from white light, we see that as lemon yellow. So, I want to review some of the things that we talked about in the color module. One is an object's black if it absorbs all colors of light. Right? If it reflects all colors of light, it's white. Right? If the object absorbs all colors except one, like yellow here, then it appears yellow. Right, and what we're seeing here, of course, is yellow. But the strip can also appear yellow, so notice we're also appearing yellow here because we're absorbing the complementary color from white light. So here, the complementary color from white light is absorbed. So indigo is absorbed. So we see yellow. Now let's talk briefly about our copper patina. When we looked at our copper patinas, we had some mix of copper with waters that were surrounding that copper. We also ended up with a mix of copper with ammonia that was surrounding it, and those gave us the greens and the blues. And so one of the reasons that we saw that is that those ions absorb orange and red light. So this is a cartoon where if you had the copper with the ammonia complex to it in solution, what you would see is that it absorbs the orange and the red light. And so that leaves the complementary color of blue and green, which is what we see with copper patinas. So if white light, like ordinary sunlight, passes through this copper ammonia solution, some wavelengths of that light is absorbed by the solution. Now, this is a bit of a simplification. It's very hard to predict with solutions what colors you're going to be able to see, but it works really well with many of the compounds that we're talking about. So this gives us an idea of what's happening. But there's another question. Well, why do some transition metal compounds have color and others don't? And so we've been talking about copper. We talked about copper patinas in lab, and we said, look, they can form these colors. And so, but when we come over here and we look at copper iodide with copper that's +1, it doesn't have any color. And when we compare that to copper nitrate here, which is copper with a +2 charge, it's this beautiful blue. And so the burning question in your heart, I hope, is why? Why do some copper complexes give us these really beautiful colors, and why are some colorless? And the answer is it depends on their atomic structure. Right? Specifically, electron excitation. So remember, the electrons are outside of the nucleus. And one of the things that can happen is when these metals are exposed to light, the light is absorbed by the metal complex and it can excite the electrons. So the electrons are when they're in their normal state, they're in their ground state. And when they're excited, they go to a higher state, and that gives rise to the color that we see. So, for example, this compound, if it absorbs light at 625 nanometers, we'll be able to see it at about 460 nanometers. So that what we see here is the amount of energy an electron is excited by corresponds to a wavelength of light. And if it's visible light, that's what we're able to see. So Now, maybe the question is, well, why do some metals give different colors or no color at all? What is it about how their electrons are excited where we see these different colors? And the answer really lies in their atomic structure. And so we're going to dig into that in the next screencast.